Welcome to the Explainer. Today we're going to completely flip how you look at database modeling. I want you to just imagine for a second that you aren't staring at cold, hard rows and columns of data, but instead you're organizing this massive, intricate family tree. Because every single piece of data has a lineage, right? It has a parent, and sometimes a whole lot of children. And when we finally grasp these family dynamics, we literally unlock a totally new level of database design.
Okay, so let's dive right into this. Have you ever actually wondered how a database knows that a sedan is a car, but not all cars are sedans? Or, how it tells a sports car from a coupe, while still knowing they both belong parked in the exact same garage? Well, this is the fundamental problem of data hierarchy. We really need our systems to understand both the super broad categories and the incredibly specific details of real-world objects. And we got to do it without repeating information or just causing total chaos.
To solve this, we're going to follow a pretty straightforward roadmap today. We'll start by upgrading to ER diagrams, then we'll look at superclasses and subclasses, explore the power of inheritance, check out 2 approaches to building these things, and wrap up with ERD rules and constraints.
All right, moving on to Section 1, upgrading to EER diagrams. We're officially stepping out of traditional database modeling and into a much more advanced, nuanced system.
So if you've spent any time with standard ER diagrams, you know they're fantastic for mapping out basic entities. But EERDs, Enhanced Entity Relationship Diagrams, these really take things to the next level. Think of it kind of like a biological taxonomy. It lets us take a general entity type, the parent, or what we call the supertype, and meticulously break it down into specialized entity types, the children, or subtypes. Basically, it's a way to perfectly mirror the messy, complex parent-child relationships we see out in the real world directly inside our database.
Basically, an ER diagram gives you everything you already love about a standard ER diagram, but it comes packed with superpowers. We're talking attribute and relationship inheritances, category or union types, specialization and generalization, and of course, subclasses and superclasses. These are absolutely crucial tools that let us map out crazy real-world complexities without even breaking a sweat. Let's roll right into Section 2, superclasses and subclasses. Now we're getting into the actual core building blocks of our data family tree, the parents and the children. Let's get these defined super clearly. A superclass is really just a generic entity type that connects to one or more subtypes. The subclass, on the other hand, is that specific group of entities with its very own unique attributes. If we bring it back to that car example from earlier, the broad generic car is the superclass parent, right? It holds all the traits every car shares, but the sports car, the sedan, the coupe, those are our subclass children. Sure, they're cars, but they have their own totally unique distinguishing features.
Take a look at how this is structured. Right up at the top, we've got our generic parent, the superclass called shape. Now, every shape has certain basic properties, right? But as you follow the lines down through that little circle with the D, you'll see the family tree branches out into highly specific children, the square, the circle, and the triangle. These are our subclasses. They all proudly belong to the shape family, but a circle explicitly needs a radius attribute, whereas a square needs a side length attribute. They're totally unique children born from the exact same parent.
Which brings up a great question. How exactly do those traits pass from the parent down to the child? Let's get into Section 3, the power of inheritance.
Inheritance is, without a doubt, the single most important feature here. Just like you might inherit your mom's eye color or, your dad's hairline, a lower-level entity naturally inherits the exact attributes of its higher-level parent. So if we set up a superclass called person with attributes like name, age, and gender, any subtype we snap on below it, say a student or a teacher, is going to automatically inherit those exact same attributes. We don't have to redefine them every single time. The system just inherently knows.
Now, what's really interesting about this setup is how efficient it gets. Picture the generic employee box sitting at the top. Imagine an employee. Let's call them E101. Because the employee number and name are attached to that top-level superclass, E101 gets those basics totally automatically. But when you look down at the salaried employees subclass, you'll spot annual salary. Only salaried employees get that specific attribute, while contract employees would get something like a contract number instead. So E101 grabs the generic info from the top, but keeps their specific salary data tucked away in their own specialized subclass box. It's just a brilliant way to organize things.
So now that we know what these structures actually look like and how traits get handed down, how do database designers go about building these intricate family trees from scratch? That brings us to Section 4, 2 approaches to building. Database designers generally lean on two main methods: generalization and specialization. Think of generalization as a bottom-up process. It's literally like building a tree, starting from the scattered leaves and working your way down to the solid trunk. We take a bunch of specialized entities, figure out what common attributes they share, and bundle them up into a higher-level general entity. Specialization, on the flip side, is a top-down process. We start right at the trunk, the high-level entity, and divide it outward into branches, creating lower-level subtypes based on what makes them absolutely unique.
To put that into perspective, imagine we start with a generic person at the top and say, hold on, we actually need to separate our engineers, our doctors, and our professors because they all have totally different attributes. Well, then we are following that top-down path of specialization. But if we started with a chaotic room full of engineers, doctors, and professors and suddenly realized, hey, wait, these are all humans, let's group them under a general person category, we'd be following the bottom-up path of generalization.
Okay, so we've built the tree, we've passed down the data genetics, but let's be real. Every functional family needs some strict ground rules to keep things from falling apart. Our data family tree is no different. Let's tackle our final topic, Section 5, ERD rules and constraints.
To actually capture and enforce real-world business logic inside our database, we absolutely have to rely on constraints. The two biggest ones we pull from our source material are constraints based on membership, which is known as the disjointness constraint, and constraints based on participation, known as the completeness constraint. These rules are the law of the land. They dictate exactly how entities are allowed to behave within their respective families.
So the crucial point here is understanding membership, specifically the difference between the disjoint rule and the overlap rule. Under the disjoint rule, an entity can only be a member of one single subtype. It's strict separation, no mingling allowed whatsoever. But under the overlap rule, an entity instance gets to play the field. It can simultaneously be a member of two or more subtypes at the exact same time.
Let's actually look at that disjoint rule in action. Notice that little letter D sitting right inside the circle that joins the patient supertype to its inpatient and outpatient subtypes. That D literally stands for disjoint. It acts as a strict enforcer for a real-world business rule. At any given second, a patient has to be either an inpatient or an outpatient. There's absolutely no way they can be both simultaneously. This mutual exclusivity is a lifesaver. It ensures a hospital database doesn't accidentally charge someone for an overnight bed while also flagging them as a quick walk-in visitor. That tiny D keeps the data beautifully organized and strictly honest. And wow, that brings us to the end of our structural journey. We have seen exactly how enhanced entity relationship diagrams give us the power to categorize literally everything, from sleek sports cars to hospital patients, using incredibly clear hierarchies, clever inheritance, and super strict constraints. It's just a ridiculously powerful way to bring order to pure chaos. So I'm going to leave you with this thought. If you could apply this top-down, structured way of thinking to all the messy, scattered data of your own everyday life, what would your superclasses and subclasses actually look like? Something to think about. Thanks for tuning in, and keep exploring.